All right, so we're going to pick up right where we left off last time. We were designing this list-based data structure, or this list data structure based on arrays. So it was an array-based data structure. And it was dynamic, and it grew, and maybe it even shrinks when we take stuff out. We started with some basic functionality here of adding things, putting things in, retrieving things, removing things, basic CRUD, right? Create, retrieve, update, and destroy. Just like we did with SQL, putting stuff into a table is very much like you would with a data structure. Remember, we are online, so if you have any questions, go ahead and post to the YouTube live stream here. Otherwise, let's go ahead and remind ourselves which methods we actually made. So we're keeping track of everything in this integer array, right? And then we've got also the size, because the size of that array, say that there are 10 slots in that array, that's the capacity. But if you only put 3 things in there and you've got the capacity for 7 more, you need to keep track of the actual size. We initialize it to 10. When we add an element here, we first of all check to see if it's full, right? If the capacity here, the length of the array, is equal to the size, in which case we grow the size of this to accommodate this new element. We add the element, and then of course we increment the size. We also implemented this add element to add a particular index, right? What's the problem here, though? That's where we left it off, right? We'll come back to that here. A get element at a particular index, which makes some basic error checking, and then returns the element if it's not there. We've got a get size method and then a toString method. All right, so shift stuff down. Oh wait, shift stuff down from index to shift stuff up is what I should have said, right? Yeah, we're shifting stuff up, starting from the end and working up to the index. This is where we left it off. What am I not doing in this method that I am doing up here? I'm not checking the capacity, right? If this thing is full, can we, if it's full and all 10 elements are here, can we shift these 5 down in order to make room for an 11th one? No. So I'm going to go ahead and cut and paste that stuff. There we go. Good idea, cut and paste, cut and paste. Probably there's a better way of doing this, all right, so help me out. Which one of these methods is more general? Right? The one that adds stuff at the end, or the one that can add stuff to any index, period? Probably this one, right? This is going to be more general. So I'm going to make it so that I'm going to change this method, right? Remember, all we're doing is taking this piece of code and this piece of code, and we're doing it right here, and we're doing it right here. The only difference is that we are shifting stuff over to make room for it. I'm going to remove this method's implementation, and I'm going to phrase it in terms of the other method. This dot add element at index, We're going to still add x, but which index are we going to put it at now? If you're always adding it to the end. If there are 5 elements in there, then where's the end? 0, 1, 2, 3, 4, 5. So we will add it to this dot size. Right? Much, much simpler, right? Now I have one method, and I could probably, add a whole bunch of other methods at this point, right? Public void add element to start, right? Int x. Do I have to worry about implementing this at all? No, all I have to do is call that other function now. Now it's not going to be at the start, it's going to be 0, right? Added at that index. It'll shift everything over for me, automatically make sure that it grows if it needs to, and then it will actually add the element. Right? All of that's being taken care of by this one method now. All right, let's go ahead and test it. Let's say add element, add element, add element. Let's go ahead and run this, make sure there's a regression here, that we changed stuff. Did we break anything? No, we didn't. Right? Let's go ahead and add an element at index, say, -1, though. Is that going to be valid? Probably not. Right? In Python or something like that, that would be valid. Why? Because in Python, lists wrap around back to the beginning. So if you put it at -1, where is it going to be? Here's 0. If you put it at -1, where's -1? It's just going to wrap around to the end of the list. Right? But that's not how Java does things. So we're getting an array index out of bounds exception here. What if I wanted to add it to, I don't know, 100? That's also going to be an array index out of bounds exception. So we should be making sure that we're taking care of that stuff very, very quickly inside the class. I'm going to steal this code up here and cut and paste it. Right? Now let's think about this though. Certainly if there's a negative index, that's not good. What about this right here? Should we be allowed to add elements to index size? Right? So remember, 1, 0, 1, 2, 3, 4. Can you add something to index 5? Sure, that's just adding it to the end. So if it is strictly greater than the size, then we'll throw this exception. If you ask for something that doesn't exist, right, that sixth element, when there are only 5, then we're going to throw that back at you there, but we're going to have a different criteria, slightly different criteria over here. In fact, cut, paste, maybe there's a better way of doing that, putting it into a function, check indices or something like that. You're going to have a little bit of a different implementation, but okay, you might want to consider consolidating that. Now over here in my demo, I'm going to get an actual error message here, invalid index 100. Let's go ahead and restore that. And it's all good now. Right? I think it was 5 before, I'm not sure, who cares. Right? All right, great. Let's continue. I need a way to remove things. I need a way to modify things. Right? Let's go ahead and do it the easy one here first, modify things. So what I'm going to do is I'm going to replace an element. Public void for now, replace element. And I'm going to make this more general at index. Right. So it's going to replace y with x, int index. There we go. So let's document that. Replaces the element at the given code index with x. And I'll codize that too. There we go. All right. So is this enough? This dot array of index is now equal to x. Well, do I have to expand the array? No, because if you're taking something out, throwing it away, and replacing it with something else, it doesn't need to grow, it doesn't need to shrink. What else, what do I need to check though? Do I need to say size plus plus? Or minus minus because it's going down? Nope. I could go size minus minus and then size plus plus. That's kind of stupid though, right? What do I need to be checking? Indices. Right? Are these valid indices? And at this point, I'm going to really strongly recommend that we put that into a method, but I'm not going to do it. Right? In fact, I'll do what any good programmer does. I'll put in a to-do. Consider creating a private index checker. There we go. Why would I want to make that private? I do not want to expose the internal workings of my class to the outside world. That's called a leaky abstraction. You're leaking details to the outside world about how it's done, potentially giving them an avenue for screwing around with the internal workings, right? You want to make sure that you're only giving access to public methods that you intend for somebody else to use. If we're going to be checking the indices inside the class, that belongs in the class. Good encapsulation stays in the class. Okay, that's pretty good. What else? Oh, actually, before we do this, if you replace something, okay, go ahead and put x where y is. What happens to y? At this point, with this design, y is just thrown away. How could we make this a little bit more accommodating, a little bit more flexible to the outside world that's going to use this stuff? Here you go. Replace y with x, and then give me back y as a return value here. Right? So to do that, I need to save it off. Int temp is equal to this dot array of index, and then I can return temp. There we go. Wonderful. So I've got a way to add things, retrieve things, modify things. Let's add the last piece of the puzzle here, a way to remove things. So public, and we'll go ahead and say immediately that we're going to return it because I want you to take out that guy right in the middle there, but I also want you to return it back to me. Right? We'll take out that middle element and then shove them all together so that we're not wasting space. Int remove element. Remove and return element at index. That's implied. Int index. There we go. to do add documentation later on. Right? So what we need to do is, of course, check, is this a valid element? Right? And for that, I'm going to, yet again, steal this code and do some index checking here. Right? If you ask for something that doesn't exist in either direction, then we'll throw it back at you. Right? Otherwise, let's go ahead and save it off. Int temp is equal to this dot array of index, and then we'll return temp. Right? But what do we now need to do to make sure that we're not leaving that gap right in the middle? We need to shift everything down. Right? So again, visually here, if we've got, say, an array that looks something like this, and it's got, say, 10, 20, 30, 40, 50, and then the rest of this is unused, right? And we want to remove 30. So we've saved it off so that we can return it eventually later on, but we don't want this gap here, right? We don't want a missing element. So what I need to do is I need to take all of this stuff and just do the opposite of what we did on Wednesday, where you shift everything up to make a room for something. Now we just need to shift everything down. For this, I will start right there, right? Actually, I'll start at, say that this is index right here. I'll start at index, and then I will copy this element over here. Then I'll copy this element over here, copy this element over here until I get down to the end. That's pretty straightforward. In fact, it's more straightforward than what we did on Wednesday. For int I equals index, I is less than something, you'll help me with that. I plus plus, we are actually going up now this time. This dot array of I is equal to this dot array of I plus 1. It's just the opposite of what we did on Wednesday. We're shifting things down now, okay? What do I go up to? Do I need to go all the way to the end of the array, this dot array, dot length? No, not necessarily all of them are being taken, right? This dot size. Right? So let's think about that. If there are 5 elements in there, 0, 1, 2, 3, 4, and we want to remove this one, I'll start here and copy this one over. Copy this one over, right? That's certainly going to be enough. Is it going to be too much? Potentially, right? -1. Think about that. Think about it with this particular example. You want to remove index, index is equal to 0, 1, 2, 3, 4, right? And then the rest of it is garbage. And here the size is 5 because we had 30 in here originally, okay? So the index here is that we want to remove it from 2. So if I start my I at index, and then I go index plus 1, index plus 2, right, dot, dot, dot. And the index here originally was 2, so plus 1 would be 3, plus 1 would be 4, dot, dot, dot. Where do I need to stop? I need to copy over this 1. I need to copy over this 1, and then stop, right? So in other words, I need to stop at index equals 3, which is size minus 2, right? But if I'm going to use this strictly less than, then I just need to say -1, okay? All right, so let's come over here and try to see if it works, right? Numbers dot remove element. Let's go ahead and remove 60, which would be at 0, 1, 2, 3, 4, 5, 6, at index 6. And also, let's make sure to capture that value, right? Because we're removing it. System.out.println at y to make sure that we remove the correct element, but then also let's print out numbers and see what it looks like here. Remember that it's going to be, well, it'll print out again here. 10, 20, 30, 40, 50, 101. 70 through 42 has now been shifted down. It looks like it works to me. Uh-oh. We have another 42 introduced here. What did we forget to do? So if you have 5 elements before, you take one out and you shift them down. How many elements do you have now? 4. So therefore, this dot size minus minus. Here's a cool trick. You could have done that up here and then clean that up. Right? Either way, I'll leave it like this. Right? Run that again, regression test, yep, now it passes. Of course, I should not be doing any ad hoc tests. Yes, when you actually develop, you do some ad hoc testing just as a sanity check. But ultimately, you want to write a bunch of JUnit tests so that it's repeatable. So when somebody comes in and mucks around with the stuff that you wrote before, you can run those tests and say, nope, you broke it, right? And that's why that's called a git blame, right? We blame that person for checking that stuff in. Actually, you don't even let somebody check buggy code in. If it doesn't pass all the tests, it doesn't even get checked into the repo, right? Okay. Looks good so far. I like all this stuff. One thing that we could do that I'm not going to, because you probably understand how to do it at this point, I'll put in a to-do here so that when the code gets posted, you'll remember. Think about possibly shrinking the array if necessary. Or if necessary being, the criteria that we have is once we're full, we increase it by a size of 10. So we go from 10 to 20, 20 to 30, 30 to 40. Well, what happens when you remove a bunch of stuff? And you've only got 5 elements in here, but you're taking up a megabyte of information. Do you want it to shrink then? Yes? No? That's a design decision that we'll leave to you. Okay? All right, great. I have accomplished the goal of creating an integer-based, or an array-based list, dynamic list, that is good for what? Integers. Is everything an integer? No. It can be, right? Everything at the end of the day is a 0 or a 1, right? So technically, yeah, you just solved all the problems, but no, not really. Let's go ahead and cut and paste this. I'm going to have a my double, or actually a string. Let's go with strings. My string array list. There we go. Now I've got one for strings. All I need to do is go through and change every instance of integer to string, right? My string array list, now it's an array of strings. Great. Add element, we're going to add an element x here. Add element at index, we'll go ahead and to start, let's see that. Add element at index takes a string instead of an integer. It returns a string there, and therefore temp needs to be a string. That's great. Anything wrong up here? String, nope, that's good still. Probably something else going on. Integer temp, there we go. Remove element at index. There, that's good. Let's fix this up. Add element at index, there we go. There's that x. Nothing else needs to change there. And then the return type here is get element at index. All right. Did I make any meaningful changes to that code? Here's another trick that you might want to use sometime. If you highlight 2 files, you can right-click and compare with each other. Right? It's kind of like a git diff, and you can see the differences between these two. Let me go ahead and expand that out. Do you see any significant substantive differences between these two classes? No. All I did was change a bunch of ints to a string. Let's do better. Oh, by the way, another trick is you can compare with local history. So if you're not, well, first of all, if you're not using git and checking things in regularly, get in the habit of using git. No pun intended. Right? That is the standard. If you haven't been using git, you need to start. Right? But here's the poor man's git, right? Where we didn't actually commit anything to this. Looks like, let's see, this morning at 10:46, so it only kept track of like, oh, that's because it's brand new, right? That's when I created it. But it's been keeping track of at least 10 saves that I've manually saved. That's not that interesting. Let's look at the one from, say, let's say, compare with local history there. There we go. That's some local history, right? There's an, so you make a change, right? You broke something, and you didn't check it into Git, right? What did I break? When did I break it, right? Yeah, at least you can look at the local history here back to, looks like Wednesday when I created it. Right? I'm sure that if I looked at even older files, the history would be even longer. Right? And then you can compare it by simply double-clicking, and there's the change that I made that day. Right? Go ahead and get rid of that. Okay? All right. So let's solve this problem once and for all, because I do not want to copy this into my double array list, my invoice array list, my blank array list. actually, I do want to change it into my blank array list. Let's go ahead and do that. Copy, paste, my, not string array list, but my array list, period, right? And let's go ahead and open that up. And I'm going to change this so that it's parameterized. This goes all the way back to Lab 6 in our object-oriented programming principles, right? Remember, up till now, we've been focusing on encapsulation and abstraction. Now I'm going to put in a little bit of polymorphism here to solve this problem once and for all and forever, right? It's not going to hold an array of strings. It's not going to hold an array of doubles. It's not going to hold an array of integers. It's going to hold an array of t's. Right? So that when you create my array list, you parameterize it. This particular instance will hold strings. That particular instance will hold integers. Right? That changes into t's. We'll come back to that because it's not correct. Right? That changes into a t. That changes into a t. Everything that I change from an integer to a string will now just simply be a generic t, right? I don't even have to change any of my documentation because I made sure that it was generic, right? T, there we go. We're not going to return a string, we're going to return a t. We're not going to take a string, we're going to take a t, whatever that is, all right? And finally, we're going to return a t. There. So now we do have to deal with this. The reason it's not going to let us do this is because of memory issues. So those of you coming from a C background will immediately recognize this problem. When you call malloc to allocate memory for, say, 10 integers, do you say that I want 10 integers? Nope. You say, I want enough memory to hold 10 integers. Right? So 10 times the number of bytes that each integer takes. And how many bytes does each integer take? Nope, minimum of 2. 4 usually is the standard. Same as Java. But now what if you wanted an array of doubles? Right? As the name implies, does it take 4 bytes? No, it takes 8 bytes. So let's use a generic type here. How many bytes does that take? Who knows? The compiler doesn't know. That's why what we have to do is we have to force it to understand what it does understand. Or we're being forced to speak its language. This is going to be an object array, okay? An object, it does know about objects. Every object is a reference, and it takes 8 bytes, I think it is. I can do this now. But the problem is, that's not what you have up here. Well, I could do something like this, but then that breaks everything else. As you can see, we're not even going to look at it. That's not what I'm going to do. Instead, I know from my interface that it's safe to force this to become a T array. Right? Why? Because look at the interface. Are you able to, let's see, where's add element. Are you able to add a string if you parameterize this for doubles? Nope. You are forced to, you said that you're going to create this array, this list, and it's for strings. Therefore, this ends up getting replaced with string, in a sense. And you're not able to put in integers. I'll show you. Let's come over here to my demo class over here. And let's change this so that it's not my integer array list anymore. It's my array list, parameterized for integers. There we go. There. And you don't need to use that. Did anything change? Nope. But am I able to say add a string to it? Numbers.add, hello. Nope, the compiler is able to detect this and says, wait a second, you parameterize this for integers, you're trying to add a string. Nope, no go, no compile. That's why it's safe to do something like this. Force it to become an array of strings, or force it to become an array of integers, or force it to become an array of foo, right? Whatever foo happens to be. Right? If I didn't have a good interface, then this would be dangerous, right? Because this is typecasting, and remember, you've got that triangle. One is covariant, which is always safe. One is contravariant, which this could potentially be right here, which is potentially unsafe. Right? Then the other one is invariant, which is never safe. Okay? Wonderful. What I'm going to do now is get rid of those two other terrible, terrible implementations. Right? My integer array list, my array list, right? It can be for numbers, it can be for strings, it can be for everything, anything. I've solved that problem for the rest of my life. I never have to implement this again. Right? Except that there's still a problem here. Right? And this is going to give us the next iteration of this. For this, let's run some experiments. So if you're interested, you can go ahead and create a long start time here, which is system. What I'm doing is I'm getting the current system time in milliseconds, and then I'm going to do some load testing here. I'm going to go ahead and put in a whole bunch of things. Right? I'm not going to go for I from 10 or whatever. I'm going to go from I equals 0. I is less than, say, n, and I'm going to pump this up to 1,000. Right? And so I'm going to add 1,000 things in here, I++. And I'm just going to add it to the end. At the end, I will record my time again. End. And then I'm going to print that I'm done. I'm not interested in printing this out because I know what's in there and I know that it works. Done. And it took %f seconds. End the line. Print f. There we go. All right. And I'm going to have end time minus start time. And because it's in milliseconds, I want it in seconds. I'm going to divide by 1,000. There's my experiment. Okay? Let's run this and see how long it takes. Oh, wow, that was fast. I wonder how far we can go up here. 100,000. It was noticeable, but now it's a half second, right? Not that big of a deal, right? So let's kick this back down to 1,000. And instead of adding an element at the end, let's add it at a particular index, at index. There we go. And let's run that again. Oh, well, that's almost what it was before. What was it before? 0.001? 0.004? There's statistically no difference between those two. But let's kick this up to 100,000. What was it before? Half a second? There we go. 13 seconds. Why? Why was that performance so terrible? By the way, do you think 100,000 is anything? No. This should be way faster. So just well, OBS here is taking like, it claims that it's only taking 8% of my CPU, but the fan says otherwise. Right? So 100,000, no, that's not anywhere near big data. So what's going on here? Think about somewhere in the middle of the algorithm, where we've got a huge array here, right? And there are, say, 50,000 elements in there. And you're wanting to add it to the front of the list. What are you going to have to do? Move 50,000 elements down by 1. Right? Individually. And on the next iteration, now there are 50,001 elements to be shifted down, then 50,002, 50,003, ... All the way down in the last iteration, you've got 99,999 things to shift down. Previously, you had that the whole individually all the way down to 0. Right? The math of that is going to be n squared, but we'll get to that later. Right?
Well, I mean, like, I want to see factorial of that.
It's not factorial, it's just n squared. Right? Okay, so can we do better? Not with this list. And this is why it's important to understand the difference between fundamental data structures. We need something different. That something different is going to be called a linked list. A linked list is different. It doesn't store things into an array. Instead, it stores them into what we're going to call nodes. Right? A node is going to have two things. It's going to have 10, the element, right? This is the element right here. And then it's going to have a reference to the next node, which is going to be very much similar to the other one. There will be 20, say. That will have a reference to the next node. Do you see immediately why we call it a linked list? It's a bunch of chain links together. The first one links to the second one links to the third one, dot, dot, dot. Suppose that I only have 3 things in this list. What's at the end here? For visualization purposes, I'm going to use some Greek. Right? That's Greek, right? That's phi, right? Phi. Phi is the universal indicator for undefined, nothing, right? In other words, for Java, it's going to be null. Okay? This thing is called the head of the list. This thing is called the tail of the list. Right? Just like a snake. Or, yeah, we've got the head, and then down here we've got the tail. It snakes around. Okay? Now, does this solve our problem? What if I wanted to add something to the beginning of this list? What do I need to do? Just create a new node, make that node point to the head, and I'm done. Do I need to shift all of this stuff down to make room for it? No. This might solve our problem. So let's go ahead and start designing this. The first building block that I need for this is that node class. Right? And I'm immediately going to learn from my previous mistake of having to create 2 lists and realizing that there's no appreciable changes, and I'm going to immediately parameterize this so that it can hold, the node can hold anything. It can hold an integer, it could hold a string, it could hold a double. A node is represented by 2 things, the element and the next node. So the element, that's easy. All I need to do is say private t element. Right? There we go. What about the next node? Private next node. I'll just call it next. What's its type going to be? Well, it's referring to a node, right? Well, what is it? What's a node? A node. Right? This kind of looks like recursion, but it's not. It's kind of like a self-referential composition. You can do this fine. You can do this in C, you can do this in Python, you can do this in any language. Right? Because I am myself. I can own an instance of another person, right? Of an instance of another object, that is, right? You can't do that, right? Thankfully, you can't do that. Right? All right. I was thinking about the person class there. Right? Anyway, private element T, private element next. We need a way to create this stuff. So, what? Constructor, right? Public node. How do you want this default node, this constructor to behave? Does it make sense that you would want to create a node with nothing in it, first of all? Maybe not. So at least you'd want this element here, 42. But what about this right here, the next reference? I don't know. Maybe I want to set that later on. So let's go ahead and set this up so that we're taking an element of type T, element. This dot element is equal to element. There we go. And this dot next is equal to null. I don't know what I'm pointing to next, right? But there's this element inside this, this node, and it's pointing to the next node, but I don't know what that's going to be yet. Let's go ahead and generate a bunch of things automatically here. I'm going to expand these both out. And I want you to be able to get the element and even get the node maybe, and even set the node, because if I don't know up front what you want to point to, maybe you want to point to that node over there or that node over there for the next, right? Then later on you'll be able to set it. So let's go ahead and generate this. If I'm never changing the element, then I'm going to also make that final, because it's best practice. Maybe I'll have a very good reason later on to change this. I definitely have a very good reason right now to not make this final, because I want you to be able to set the next node. Okay? That's pretty good for now. Let's come back to that later. We're going to add on to that as we go along here. Let's go ahead and create our myLinkedList class. And immediately it's going to be parameterized, the same parameterization as the other one. How do I represent this list? Should I keep track of every single node? What if I did? That's called an array, right? And I'm back at square one. You don't want to keep track of every node. which node do you want to keep track of? Probably the head. Because if you've got the head of the list, you can get to any other node. All you need to do is traverse to the next node. You want the last node? Just keep going until you get to the end where you see phi over here or null. Right? But I'm only going to keep track of the head of this list. So private node t head. Right? That's it. That's the representation of my linked list. Now, of course, I don't have any bells and whistles here. Right? I don't have any of the add functionality, retrieve functionality, remove functionality, and modify functionality. I'm probably going to want to go over to my other class here and cut and paste every single method over here and then change it so that it conforms to that other, they're basically the same list as far as their interface is concerned. That there's a way to get the size, there's a way to get the element at a particular index, et cetera, et cetera, et cetera. That tells me that maybe I want to rethink about what we're doing here with respect to object-oriented programming. What's missing here? We've got encapsulation, we've got abstraction, we've got polymorphism. What don't we have? What's the other fourth one? Inheritance. There we go. So how could we use inheritance here to have a common interface? What I'm going to do is I'm going to create a new interface, and it's a MyList interface. There we go. And the way that I'm going to do is I'm going to copy the entire interface of this other list that I made, maybe even the documentation, not the toString method, but I will put it all in here. Now, that's not what an interface is. An interface does not, it has default methods, but don't worry about that. That was a mistake in Java. It has interface. It has function signatures, method signatures. So that anything that implements this interface will have an add element method, an add element to start method, a replace element at that particular index method. There we go. Get rid of the implementation, and you are only left with the interface. Get rid of the implementation, and you are left with the interface. There we go. There we go. And there. There's my interface. And now I can come over here to my integer array list and treat it like that interface. Implements my list of elements of type T. Why is this good? Because over here in the demo, I can change my integer array list to my list as an interface. And this is looking a hell of a lot more like what Java does, right? Because that's what we're redesigning what Java did from the start. Right? And I can take out this implementation and I can say my linked list. As long as my linked list is implementing or implements my list of T's. Right? All great over here. All I need to do is change this one implementation. And I've got an array list versus a linked list. And we're going to see if that does a lot better. Obviously, I need to make sure that I am implementing everything. I've got a lot of work to do. Right? We're definitely not going to do this in 12 minutes. But let's go ahead and do the low-hanging fruit, the easy stuff. What about get size? How do you determine the size of your list? Well, let's think about this algorithmically. The size of this list is 3, right? So all I have to do is start at the head and say 1, go to the next one, 2, go to the next one, 3, go to the next one, uh-oh, now we're at phi here, it doesn't exist. What did my counter just say? 3. Right? All right, that's easy enough. Let's go ahead and implement that. So the idea here is that I'm going to keep track of a current node, current. Okay? I'll start at the head, and then I will go until current ends up being null, keeping a tracker as I go along. To go from one node to the next node, all I need to do is access its next value and update the current node. So, node t current. Right? I will start where again? at the head. Keep a counter. Count is equal to 0. Initialize it to 0. Why? Because it could be an empty list. In fact, it is an empty list, right? What happened to our constructor? Oh, we didn't have a constructor. That's right. We probably need a constructor. We'll come back to that as the other low-hanging fruit. All right. So while current is not equal to null, we will traverse to the next node. All I'm going to do there is current dot get next. That gives me the next node. Now I just need to simply replace the current with it. Current, right? Here, I'm pointing to this one right here, and it's pointing to another node. I'm going to get that node and then move my pointer over here so that I'm referring to that next node there. What am I not doing? I need to increment that counter, plus, and return count. Now think about the edge case here. What if it is an empty list? The head is probably going to be null. So does this while loop ever execute? Nope. And we return count, which was initialized to 0. That seems like it works to me. Let's give ourselves a constructor, public my linked list, so that we initialize head to null. There we go. And let's test it over here. Obviously, I'm not going to do all this, so I'm going to go ahead and get rid of this just for now. All right. And I will, not this part, sorry. And let's go ahead and say numbers dot size, get size, system dot out dot println numbers dot get size. I would expect 0 here if this works. Hey, it works. Now let's try to put something into it. Obviously that's not going to work because we don't have that implemented yet. But we can. Before we do that though, let's think about, that's the interface. Let's think about this implementation that we just did. Do we really need to do that? Is that what we did with the array list? No, with the array list, we kept track of the size. Anytime that we added something, what did we do? We incremented it. Anytime we took something away, we decremented it. Why can't we do the same thing? Return this dot size. Oops. Yeah. Thank you for your suggestion, Eclipse. What would that do? Let's try it. Ah, exception. What happened? Infinite recursion, and therefore, at some point, we run out of stack space, and we get a Stack Overflow. That's why that website is called Stack Overflow. It's just a programming joke. Right? So this dot size. There we go. Not size. Quit auto-completing. I know better than you. Right? All right, so that means that we need to keep track of it. Private int size. And in our constructor, we will initialize it to 0. Technically, I should do this dot. There we go. All right. Is there any easy thing that we can get done in the next 5 minutes here? No? Add element to start, replace element, add element, get element?
All that seems like it would follow the same model if you did the index where it's
Yeah, it does seem that there's a common theme here, right? Traverse to a node at a particular index, because you might want to get it, you might want to replace it, you might want to add to the end of it, or add right before it, or something like that. It does seem like I should be able to write some general function that traverses to a particular node and gives you that node.
And then if you have that, you can just put it in literally everything else.
Yep. Exactly, right? But we're not there yet, and we're not going to do that in 5 minutes. So instead, I'll encourage you to go to the limited number of help hours that we still have left if you're struggling with the database design. Even if you're not struggling with the database design, go ahead and stop in now, not at 4 o'clock with the last one, because I'm sure that there will be way too many people there. But you can stop by right now when it's not busy, likely. And just, here's my ER diagram. What do you think? Oh, wait, I see some obvious flaw there, right? Plenty of people have been doing that and getting help throughout the week. It's going to be difficult to do that if you're waiting to the last minute, the last hour at 4:30. Otherwise, have a good weekend, and we'll come back next week and continue from here. See.